I'm a little bit disappointed with the progress of my AngstromCraft project. But anyhow, I have to share my progress. Mm, so, mm, so in the previous video, in the last video, I shown you a sphere can be generated. So now we will move to this source strain epitaxial growth. And in the case of this epitaxial growth, the dominant surface is 111 direction and it's a family. Uh, so in the Miller index, um, so this is 111 of course. However, in this code and Armstrong Craft, everything is just aligned to the simulation coordinate system. Here x, y, z are not exactly equal to 100, 010, 001 direction. Actually, this is tilted 45 degree to match the most widely used uh, coordinate system in microelectronics. So, of course, there is no written convention, but I have done it up to now with the implicit assumption on that coordinate system. So that's the reason why here we have quite stringent numbers 41, 0, 29. That is corresponding to the 111 surface. So that is not the exact one, but the error is quite small, so we can safely use it for our purpose. And here I set the bandwidth of 10. Bandwidth of 10 means that I will just consider 10, 10, 10 for an octant as considering range of my calculation. And I think that this parameter is quite important. So this is the ratio between the growth velocity along 111 direction and 001 direction. So although there is not many reports on this number, so but I will just use this 0.6 for my own purpose. So now this one just to generate a certain model, and by applying this model only once we will have quite a large expansion of our system, and I will just do it twice so it will expand quite a lot. So let's just start from our initial .cgns. This initial.cgns file is generated to mimic the very initial stage of our source drain epitaxy. So now let's just have a look at it. Initial.cgns. In this case, yes, what is this? These two walls are corresponding to nitride, and you know that is corresponding to the spacer. And now you can see there is a certain part, V-shaped one, and that is actually the silicon. So what is it? Here, in this part, we have a fin, and also in this part we have a fin. However, this uh, intermediate region between one dummy gate and another dummy gate, that is etched away. So now we have this initial silicon area, and from this silicon area we will try to grow silicon germanium region, although I will just use silicon for that reason. Okay, so that was initial.cgns, and let's just open epitaxy 20.cgns. So the number is only for my own purpose. So yes, there is another one, and just eliminate nitride. And now share share the camera. Okay. Okay, now you can see that in the left panel, you can see the initial structure. So there was only okay, there was only silicon, and after that we tried to make anisotropic epitaxy, selective epitaxy, and now we have the shape looks like this. So here we have a certain surface, very clear one, and this surface is corresponding to 1 direction. Also here we have a same surface, and also here we have a same surface, and this is here we have another one. This is corresponding to 110 surface, but it is originated from our fin itself. And also here we don't have any kind of 111 because the structure is quite ideal, and in reality we have a certain slopes and 111 surface once again. Well, this is the initial stage of my code development, and in reality, so let me just discuss what is wrong in this implementation. First of all, here you can see that the height or overgrowth of our source drain is quite a lot. However, in reality, nearby this position, we don't have much fast growth of silicon germanium part. So this is wrong. And also, we can see that there is a 111 surfaces, and if we perform this kind of procedure again and again, what will happen? So it will just go up and up while keeping its surface. So this 111 surface is the dominant one in my calculation and never disappear. However, in reality, so it changes the shape and eventually turned into the other way around. We will have another 111 surface. However, this is not this V shape, but inverted V shape will occur in reality. However, current implementation cannot reproduce that kind of effect because we are just considering free growth of our material. So that's the problem, and that's my headache. I have to consider more effect to reproduce more realistic one. So, yes, that's the problem. But anyway, in my opinion, improving this physical effect, or what is physical description, is quite important. But at the same time, now I have to prepare this fall semester. So somehow I have to compromise between description, physical accuracy, and numerical efficiency or lecture progress. So I will come back with more jobs for fabrication procedure for FinFET fabrication flow. Okay, thank you for your attention, and see you later.